Thanks the organizers for having me. I appreciate it. So today I'll be presenting a paper called How Inductive Bias in Machine Learning Aligns with Optimality in Economic Dynamics. It's a joint work with James Yu, brilliant PhD student at UBC Economics, and Jesse, who we just heard, and then Jeff, who is at UBC SATS, the British Columbia SATS Department and Vector Institute. There you go. So I'm going to start the talk, the motivation, by a quote. In the long run, we're all dead, and I think it's true. I'll come back to this a couple of times during the talk. So let's keep that in mind. Numerical solutions to dynamical systems are central to many quantitative fields in economics. IO, spatial economics, macro, units. Dynamical systems in economics are essentially boundary value problems. But these boundary value problems first happen at infinity. And the second thing is the values at the boundary are potentially unknown, right? And these boundary value conditions result from forward-looking optimal behavior. Examples of this for economists, you have heard it. No bubble condition, transversality condition, no Ponzi scheme conditions. These are the examples we have seen. Without these problems are proposed. In the Hadamard sense, it means the solution is not unique. Actually, for these cases, there will be infinitely many more, right? And one could argue these forward-looking boundary conditions are key limitations in scaling our problems. Because if it wasn't, I could do an initial value problem like the way we do in sciences and engineering. Take the initial conditions, iterate it forward with Euler. I can do 10,000 of those in less than a second. So with this motivation, I'm going to the contribution. First, we show that the inductive bias alignment, the minimum norm implicit bias of modern machine learning methods, automatically satisfy the economic boundary conditions at infinity. Second, we show that deep neural networks and kernel machines learn the steady state very well and accurately, so they can extrapolate outside of the interpolation region. And then we show that the robustness and the speed is comparable to the, even better, I would say, but my co-authors disagree, better than the traditional methods. And then they're way more stable than traditional methods. Stable in the sense that things don't explode. And then today's a short talk, so we have the consistency of ML estimates, the proofs in the paper too, but I'm not going to talk about the theory today. I'll leave that for a longer version of the talk. To give you the intuition of why this is happening, by the way, thanks, David, for setting up my talk. This is a fancier version of your figure in slide 5. All right, so if you need the plot, let me know. All right, all right. So there are two sides to this story. The first side is the ML side, right? Large ML models are overparameterized in the sense you have more coefficients than data points, right? So they're totally capable of interpolating your data. Beyond that, because they're overparameterized, there could be infinitely many interpolation solutions. So the question is, which one do we find if I run, right? From ML that has nothing to do with econ. The recent literature, and actually I saw Misha Bilkin has a talk tomorrow here as an invited speaker. He has done a lot of work on this. Recent work has been shown that they're biased towards functions with smaller norms. They don't like explosive. They don't like large functions. They like smaller functions. I'll come back to that with more mathematical details. I'm hand-wavy a little bit right now on the intuition. On the econ side, one of the signatures of dynamical models in econ is saddle path stability. Right? Usually, there is a steady state that happens at infinity that we're looking for, and the solutions are in the sense of the black. Right? That is a saddle point that I have to find. With any deviation around it, the red ones. They are a solution of the system, but they violate the boundary condition at infinity. And they are either locally converge, explode, or globally explode. Depends on the sort of problem you're dealing with, right? So technically, you can see that these functions that are suboptimal are explosive, I think. So it would make sense to think, oh, if I use an large ML models, right, it's gonna rule out these records and give me the economic that I was looking for. That is the intuition of the working debate. All right. So with that in mind, oh, by the way, this y would be the control variable, the x would be the state variable, and this is the vector field of differential equations that we have in dynamical models and systems in econ. Sorry. With that in mind, what kind of a problem do I have in mind? What we're going to actually attack in this paper. We are focusing on a subclass of economic problems, continuous time, deterministic, infinite horizon. We have other works on different setups, but today I'm presenting this. So X is your state variable, and it's an X dimensional, and it has that following law of motion. There's this big function F that takes the state variable and takes the control variable, and then gives you a law of motion for state variables. Then the jump variable or control variables, Y, have their own law of motion. And what sets apart us about a little of classical optimal control problems is stereotypes. We have algebraic constraints, right? For example, they come from economic conditions. They come from no arbitrage condition, market clearing condition, etc. That provides a relationship between the values of X and Y, right? And the initial condition for state variables are given. For example, capital of time 0 is 0, right? And the boundary condition at infinity looks like this. There is this function b that is, so depends on time, and your state variable and control variable. And as time goes to infinity, I want the optimal solution to behave like this, give it to be 0. So what is the problem? What is the goal here? The goal is to find an approximation for the control variable and the state variable. What is the problem? The problem is, unlike many applications in science and engineering, natural science, I don't know why 0. That's a control problem. I have to choose it as the agent. I don't know. Even if I know why it's 0, right? This problem is a saddle path stability problem. Error accumulates over time. Small error accumulates, and things like that. Right, so that's the problem, sort of problems I have in mind. So the method. So here I'm looking for functions that are a function of time. This is not a state space model. To represent time, I find that interval. I'll actually choose an interval of 0 and t, capital T, to represent time. Then I sample it. That D sample. T1 time at time 1, time 2 to time n. Right. Then I pick a large machine learning models like deep neural networks to approximate the X and Y, right? It looks a little bit complicated, but the logic behind it is very simple. Right? So I'm looking for a function that minimizes deviations from these models up there. Okay. So I want, over all the sample points that I have at the time, I want the deviations of the time evolution of the state space, the first one, the state variables to be minimized. Then the evolution of time equation for the left-hand side minus the right-hand side of control variable to be minimized. Then I want this algebraic equation to be minimized, to be as 0 as possible, as minimum as possible. And the last one, it says, look, at time 0, you have to satisfy the initial condition that is given to you. So at time 0, the state variable should be equal to 0. This optimization problem has many problems. The most notable one, what happened to that B? What happened to the boundary condition at infinity? You don't see it here. Right? So we ignore this optimization that I'm going to solve. I'm going to completely ignore the boundary condition at infinity, right? As if it doesn't exist. I'm going to ignore it, right? And then expect that the implicit bias that these modern large ML methods have will automatically satisfy this. Recent work suggests that implicit bias is toward small Sobolev semi-groups. In the sense that it gives you functions, it's a fancy way of saying that it gives you functions that have small derivatives. Essentially coincides with non-explosive. Right? So this is the method.
How stable is this implicit bias?
How stable in the...
I mean, in the sense of, does it always go to this or sometimes go to this?
I haven't seen one in the examples that doesn't go to this. In this paper, we don't have it. There's another paper that is going to come out with draft soon. By the end of by 15th, that we run it on the deep learning. The paper is called Spooky Boundaries at a Distance. And then we run it with 100 seeds for all these models, and they all converge to the ones that don't violate the transfer stability condition. In that sense, I cannot give you a theoretical guarantee on the deep learning side, right? But 100 times we run it, they all converge. So also to illustrate that point, I'm going to actually run a ridgeless kernel regression on these models, right? So what I'm going to do is I'm going to approximate the derivative of the state variables with a kernel function, which is for the kernel, I'm going to use a matter kernel with a smoothness parameter nu and a length of L. Also, the derivative of the y, the control variable, I'm going to actually use a kernel approximation on it too. For the x and y themselves, then I have to integrate up to point t, right? X0 is given, I just go and plug it in. This is the initial condition problem that is given to me. This y hat 0 and those alphas are learnable. And remember, this y0 is an important thing. I have to know it's the initial condition of the control variables. Oh, beautiful. All right. So, and then I solved the ridgeless regression kernel. So the first 4 terms we discussed, nothing new in here. And then what I'm going to do, I'm going to target the Sobolev seminar. Essentially, I'm going to target the norm of the derivatives. And then put that lambda varies almost equal to 0. It's just a nudge. That pick me the functions that have the smallest numbers. That's Sobolev seminars of the derivatives, right? And this choice is very, very natural. Because again, we are looking for functions that they don't explode. We are looking for functions that they don't go to weird parts of state space, because those are the functions that violate the transversality condition, right? And then so it's a very economically intuitive choice that we are having here. And then we'll show both results. All right. To talk about applications and results. All right, the first application is the linear asset pricing. It's not that because it's a complicated problem, no. Like I actually teach it to our undergrads, my honor undergrads. The solutions are trivial, but it's very, very, very simple and rich that we can see all these elements of it. Right? So we don't need to get confused by the economic problem itself. So we can see the elements that work here. So what happens is X is just a state variable is the dividends. Imagine you buy an asset, it pays you a dividend every period or continuous in time, and it has its own law of motion. We choose linear here for the sake of simplicity. And then y is the price, and the price of this asset that needs to be found. And it has that differential equation to be determined. And then we want that price to not be explosive in the sense, I don't want it to grow faster than the e to the power of RT, right? And R is the discount rate, right? And that's that boundary condition at infinity I was talking. This is called no boundary. This is called no bubble condition. Yeah, we'll talk about this. And then X0 is given. The dividend at time 0 is given, so you can actually find the path of dividends. So our job is to find the y. So the question is, why do I need that boundary condition? Okay. For a second, let's ignore that boundary condition and just look at those two system of ODEs. Right? The solution of that has this following of that system of ODEs. Has 2 elements. F stands for price based on fundamentals, plus this exponential term and a constant here is zeta. The price based on fundamentals intuitively is just a discounted sum of the dividends you get from now to infinity. That should be the price, right? And this zeta times the e to the power RT is the explosive term because R is positive. E to the positive number as t goes to infinity explodes, right? And it needs to be ruled out. And we call it bubble because it doesn't correspond to any economic reality. Right? That zeta is loose. It's just there's no economic condition that pins it down. Right? So we have to rule it out. And then if you do a simple triangle inequality, pick any norm. Instead of the additive structure and positivity of the solutions, pick any norm. You see that the price based on fundamentals has the smallest number. So you would expect if I go to large machine learning models, without specifying that each of the boundary condition, it will pick YF from. Just automatically will do it. It rules out all of them. Well, let's actually see it. All right. So the left-hand side shows the prices. The right-hand side shows the relative errors of the approximate solution with respect to the closed form solution for the price based on fundamentals that we have. Right? The black one, I know you can't see it because they are all so accurate that they just all overlap. So I had to zoom out at the end of the extrapolation region. Right? So the black one is the solution of the ridgeless regression with matter kernel. The blue one is the solution with neural networks that there's no regularization in. And then the dashed one here is the closed form solution that I could calculate at the hand. So the closed form solution that we have. This is the benchmark solution. this vertical line here, the dashed vertical line, is the region of interpolation versus extrapolation. So there are a couple of facts here that are interesting. First thing first, without me telling you have in your space of solution, without me telling the algorithm doing your solutions, you have explosive solutions, it just ruled them out. Like how to do it, it did it by itself, right? Both you can see the neural network approximation, just ruled it out. So you kick out explosive solutions and you get very, very accurate solutions without directly imposing transversal or no ball. What is fascinating, you're like, if you believe my story, you're like, yeah, sure, then yeah. What is fascinating is, this is my training data set, right? Training grid for Tom, right? Goes up to 30. It learns the steady state because here goes to 40. Well, it's like as if I plan for my retirement 30 years from now, and then something happens, and then my life expectancy goes up, and you ask me, so how are you going to do that, right? As if I learned it, right? As if the algorithm learned it and it stays on the flat. It stays on the flat. Because again, staying on the flat is the equivalent of lowest Sobolev semi-number. Lowest derivatives, right? The moment it finds the region of lowest derivatives, it loves it there, it stays there, right? And that's an indication of that implicit bias. And both are extremely accurate. These are relative errors. Right? So how much time do I have? Oh. The other one is the new classical growth model. As we all talked about, we saw some examples of it. The job of the agent is to maximize a stream of consumption. And the reward is ln, and they have to discount, right? And then you have a law of motion for capital, and F, and the agent has access to a technology of production. And that F is a production function of exponential form, and A is less than 1, right? If you write the Hamiltonian, do the first order condition, you end up with a system of two differential equations, which this one is straight from the constraint that you have. The second one is the continuous time equivalent of the Euler equation. I would say that's the closest thing I can say, right? And this is the boundary condition of infinity. And then, and this is what we call actually transversality condition. I call all of them transversality condition, but in the literature of macro, this is called transversality condition. That says the shadow price, because 1 over consumption is the shadow price, discounted of shadow price of the holding of capital as t goes to infinity should be equal to 0. So why do I need that condition again? Let's ignore it for a second and look at the vector field of capital versus consumption, right? This is the place I want at infinity to be, and transversality condition guarantees this. So the black line in the vector field is the optimal solution. Any solution that violates transversality condition but satisfies those two, it has to end up at a fixed point, attractive fixed point, which we call at the same time sink fixed point, right? Way over here. The capital has to go to 30. That's the plot. And as you can see, this one has a lot of big derivatives. If the path has to come up here, it has to be fueled by a lot of derivatives, as opposed to the optimal solution. So you would expect, if I give it to a deep neural network for a ridgeless kernel regression, these yellow and orange will be kicked out. Let's see if that is the case. Yes, that is the case. So again, the black one is the ridgeless regression with matter kernel, the XD is the neural network, and then the dashed one is the benchmark, and the benchmark solution is a modified version of a code that I stole from David's lecture notes. By the way, thank you, David. So, yeah. When we started this project, we needed a benchmark, so we stole it from his paper, from his lecture notes. And again, the dashed one is the interpolation and extrapolation. So again, you get the explosive solution, you get the explosive solution kicked out without imposing that boundary condition at all. And you get very, very accurate short and medium run and long run solutions. And it learns the right steady state as well, the same, similar to that. In the extrapolation region, loves to stay on that flat part and stays. One might raise this question that says, oh, look, you said you don't need this long run boundary condition, but in your training, you went up to 30. So partially you need it then. Because 30 is a long period. You reach the steady state already. Right? What happens if you go up to, for example, 9, right? Short time plan, right? So that hence the title, seriously, in the short and long run, you're all dead. So let's see what happens if I choose up to 10, right? Can I still get accurate short-run solutions? And will those be kicked out or not? Right? As you can see, again, the short-run solutions, this is capital, this is consumption, this is your state variable, this is your jump variable. As you can see, both for kernel and the neural networks, you have very accurate solutions in the short run. They start deviating, yes, of course, because it likes to stay on that derivative. 5 minutes? All right. All right, so we have a lot of extensions in the paper. We have convex concave production function. It does it. And then 5 minutes, you said? Oh, okay. So I have time. There you go. All right. Okay, I can finish early. So, all right. So to conclude, the minimum or implicit bias of large machine learning models aligns with the optimality condition in economic dynamics. Right? That's the first partial conclusion. The second one, and that's what I mean in the modern or spooky boundaries at a distance. Long-run global conditions can be replaced with local conditions, usually regularization, old school regularization we do in machine learning, right? To achieve optimal solutions. So I don't need to be worried about the long run. I can replace it with the long run with a short run condition. Here is implicit though. Both kernel and neural networks approximation accurately arrive at steady states. And if we submitted this paper, for the last part, if one of the referees in this room, I apologize. There is a thing that is bothering my head, so I'm going to proceed with caution, right? If, as we saw today, in many of talks, if we are about to turn our fixed point macroeconomic problems into PRM style optimization problems, right? This is also, what would be the role of regularization? Because we know in machine learning, regularization plays a huge role. What is the role of regularization? Now I'm slipping way out of my interpolation region. I'm going to crazy extrapolation. Can be thought of as an equilibrium device, selection device. Also, in my perspective, we are going to use actually these methods. I've been struggling with this question in the last 10 months. I couldn't actually have a coherent framework of thinking about this. So if you see me outside and you want to chat about this, I'll love to, please. Yeah. And I appreciate that. And then that's the end of the talk. The paper has lots of extensions. All these questions are answered that you might have. Yeah. And you can find it on my website and it's on our website. Thank you.